Hello, friends and colleagues. In this presentation, I'd like to show you what I learned from large block testing, hydraulic fracturing, mine experiments, and some of others, particularly in the context of the presence of layers in layered rocks and the effect of these layers on hydraulic fracture propagation. I was initially inspired by this publication, J. Gordon, 1941, that he was investigating the stress concentrations at the fracture tip. And you can see by the images that this is all technology, maybe sliding ruler calculations and so on. But what he noticed is that the tensile stress at the tip of the fracture, the one that is opening the fracture perpendicular to the fracture direction, has an intensity of about 200. Whereas the tensile stress concentration that is in the direction of the fracture propagation, the intensity is much lower, it's 40, it's 1 to 5, but it exists and develops its maximum value ahead of the fracture tip. And so with that information, he proposes that if a material has an interface that is weak, such that the tensile strength of the interface, or what he calls the adhesive strength of the interface, is less than 1/5 of the cohesive strength of the bulk material, or the tensile strength of material, then the interface will open ahead of the fracture tip and eventually blunt the fracture tip and arrest it. So that is a concept that he had when he was explaining the sources of toughness in brittle materials in his book, after, of course, explaining the sources of toughness of typical engineering materials with dislocations and so on. And indeed, in biological materials, this is the predominant mechanism that we find by which the brittle media that constitutes all these materials is made tough. Human bone is a very good example. The structure of human bone is composed predominantly by these cylindrical components that are called osteons, and by the interfaces between the osteons, which is the cement line that is shown here. And it's a hierarchical structure, right? The same structure is replicated at different levels of scale. And so as a result of that, what you have is that on a person that is healthy, this is a specimen that is prepared for fracture propagation and toughness. This is the SEM of these osteons with the interfaces. In a person that is healthy, the fracture propagates with very much difficulty because the material is made very tough by the presence of these interfaces and eventually is arrested, which is good because then we can survive falls. Except that when one gets older, for the elderly, when these interfaces are calcified and the interfaces are no longer weak, then the fracture can propagate readily. Another example, which is important, is the abalone shell. A lot of the brachiopods, marine brachiopods, build their shells with calcium that is extracted from the ocean. And so the predominantly materials, building materials, are calcium carbonate, calcium phosphate, same that for the bone, which are brittle materials. And it's because of that structure. In abalone, you have these thin layers of calcium carbonate, calcium phosphate, with a veneer of organic matter in between that allows some level of shear displacement. And because of that arrangement, the fracture toughness of abalone shells exceeds in many ways the toughness of most of the materials of engineering. So it has, in fact, is considered to be one of the toughest materials. So with that in mind, what we did is to try to replicate that idea, to have a material that is homogeneous, in this case glass, create weak interfaces. So we use a diamond bit, we cut the interfaces at some angles to the fracture propagation, in this case 60 degrees, in this case 45 degrees, just to see how these interfaces will affect the growth of propagation in glass, that is an obviously brittle material. And what you're seeing here is the sheet of glass that is on top of the plywood that is supporting this round portion here allows us to put the instrumentation into the borehole of the glass that is here. And so the color that you're seeing is the plywood, the glass is transparent. But what we notice is the presence of stepovers, you can see here. and in some cases, the presence of multiple fractures, what is now called fracture swarms. Right? And is the presence of these interfaces and the interaction between those interfaces, orientation and weakness, with the fracture that is propagating that results in those effects. And so basically, what we find is that indeed textural complexity implies fractural complexity and implies an increase in fracture toughness. Similarly, we did these experiments of, actually it's a test, laboratory testing for fracture toughness with cylindrical samples that are about 2.5 inches to 3 inches in diameter, same length at the diameter, have a 1/4 inch borehole with notches that are prepared along the length of the borehole. And then the pressure in the inner hole is increased simultaneously with the external pressure at some ratio, such that when the fracture emanates and propagates, it propagates in a stable manner. And so that's a Teratech patent, and so that has been the typical way that the fracture toughness was measured at Teratech. But these are one of the first experiments that we did with layered rock. This is Barnett shell. And so to my amazement, the result of one of the tests showed this morphology of the fracture, where the fracture had turned 90 degrees here and 90 degrees again to come out from the sample, and on the other wing, 90 degrees. And all that was promoted, but these very thin interfaces that at the time, I didn't think that they were of any relevance. In fact, I remember thinking that this was a perfectly homogeneous sample. And yet, what is imperceptible created a big change in the orientation of fracture propagation. Obviously, the stress is uniform, right? It's applied radially, so the stress doesn't have much role into the orientation of the fracture, but the interfaces and their properties really control how the fractures go. The second one is more obvious. We prepare a sample such that the notches of the fracture propagation go perpendicular to the bedding, just to replicate the way that the fracture propagates in situ. We pressurize the borehole with the same procedures, and what happened was that the fractures propagate along these weak bedding planes rather than ignoring the stress concentrator that we have created. So in hindsight is an obvious one, but again, it was surprising to us that the bedding and the presence of the weak layers within that bedding really will control and overwhelm the fracture propagation. So another experiment that was a big surprise for us was this block. This is a 1 foot by 1 foot by 1.5 feet block that is instrumented with acoustic sensors for localization of acoustic events. It has a well bore. This well bore has 2 perforation locations. And really the goal of this work was to understand whether a fracture will be preferentially dominated with one perforation and the other one will never, the fracture from the other one will never occur, or with 2 fractures open simultaneously, and how would they compete with each other. That was the purpose of the experiment, and we happened to be using Manco shell. And so to our big surprise, well, before saying that, let me make sure that the state of the stress is understood. So the vertical stress is 3,000 psi and is perpendicular to the bedding of the rock. The intermediate stress is 1,500 psi. And then the minimum stress, which is in line with the orientation of the wellbore, is 1,000 psi. So there is 3 to 1 times minimum stress to the vertical stress. And therefore our surprise, because the first fracture that occurred, and we could define that because we were monitoring with acoustic emissions, the first fracture that occurred was vertical. So the opening was occurring against 3,000 psi, despite the fact that the minimum stress was at 1,000 psi. The second surprise was that the fractures that happened through these perforations were avoiding each other, which is okay. We understood that. One fracture happens, it creates a stress shadow, and therefore the other location is not the preferential one, so the other fracture happens on the opposite direction. So there are half-wing fractures that are occurring, avoiding each other. That's fine. The problem is that they were perfectly contained, even though the stress that we are applying on this face of the block is uniform. It's a uniform stress And so one would anticipate a penny-shaped fracture across the entire cross-section of the block, and yet they're fully contained. Of course, after the fact, when the block was segmented and it was a CT scan and so on, we realized what was driving this issue. First of all, there was a concretion here, which is a more densified portion of the shell. And that dense system was making the distribution of the stresses a non-uniform system. And so we are applying a uniform vertical stress on this block, but by the time the stress is propagating through the system is no longer uniform. And that complexity on the stress distribution is promoting the delamination of a fracture along the border of this concretion. So that's one. The second one that became more obvious is that among all the layers in Manco's shell, there were 3 layers that they were weaker. And so they were highlighted on the CT scan here. And you can see that the fracture was completely contained between 2 of them. So again, the presence of these 2 weak interfaces contain the fracture, the non-homogeneous distribution of the stress because of the presence of the concretion allow that. So I'm going to show you next the actual rock that we're going to show layer by layer so that we can uncover what is happening. So this is the face of the block. And then I'm going to take one layer at a time to see how the fracture develops. So on this one, the first layer comes out and you can see very clearly the concretion. You can also see the trace of the fracture that had propagated from the upper perforation and the trace of the lower fracture. Those are transverse that propagated from the lower perforation. So far, so good. I'll take this block out. You can see the surface of that upper fracture clearly. And of course, it's just contained, right? It doesn't propagate through the block is just contained into that segment. I'll take this portion, the block out, and what you now uncover is the fact that coexisting to this transverse fracture, there is a longitudinal fracture that towards the end of the block is turning into a transverse fracture. I take this upper block, and now you can see the location of the perforations and the fracture that happened on the half fracture that happened on the other direction. And when I finally take this final block, then you see clearly that there was another fracture along the entire length of the wellbore, which is longitudinal, and that is now turning into the left direction as well as on the right direction. So this fracture that is coming in is becoming a transverse fracture towards the end of the box. So that was quite exciting. A lot of learnings that we did with this block, not intentionally, but again, going back that one cannot ignore the heterogeneities of the system and one cannot ignore the layers of the system. Now, testing large blocks, larger than those, is of course convenient because one has much more real estate in order to evaluate the presence of interfaces and heterogeneities and so on. But it's complicated. It requires obtaining these very large blocks that have to be competent, so they cannot be taken just from the surface of the outcrop because of weathering and so on. So one needs to dig at least at 5-10 feet depth in order to remove the weather section and then collect these blocks and requires large equipment, large techniques. And it also requires a large system to prepare those blocks with parallel and flat surfaces and so on. Large block testing also requires to have systems for loading those blocks. So this is a polyaxial cell that independently can load the blocks with 3 directions. This is using flat jacks and has a capacity of up to 5,000 psi. And this is an example of one of these blocks. This is again Manco's shell. And then at TerraTech, we had several sensors per phase. Typically 3 sensors or 4 sensors per phase was typical, and that allows to have a large number of redundancy in order to localize with high level of certainty. So we have a program with a large number of these block tests that we tested at least 12 of those for different reasons, investigating viscosities, rates, and so on. So let me more or less describe what you are seeing here. This is the block. This block contains a horizontal wellbore. The vertical stress is going to be applied perpendicular to the bedding. This will be the bedding of the block. And the minimum stress is applied parallel to the wellbore. So that's the typical configuration of the horizontal wellbore in the field. It's cased and cemented, and then there are perforations that are done so that when we pressurize, the vertical fracture will occur, right? And then we will be investigating different conditions of the vertical fracture. But what was at the beginning bizarre and confusing is that every time that we will complete the block and we will take it out, we will observe these wings of horizontal fractures that they were at different distances from the main vertical fracture that we have created. And we were puzzled by that. Why are these happening since we have a vertical stress that is considerably higher than the horizontal stress? That shouldn't be happening. One of the ideas was that this was an artifact that was created after the fact. We finish the experiment, we unload the vertical stress, and unloading the fracture at the vertical stress will create these partings. And then the fluid that was present on the vertical fracture will then imbibe into these segments. And so that was the result of what we were seeing. And so to test that situation, we run a test, which is the one I'm showing you, with epoxy. And then we'll let the epoxy set for 24 hours before removing the vertical stress and, well, the stresses and before removing the block. And what we saw is that indeed these features were being created during the hydraulic fracturing process. It was not an artifact of unloading. This was done in 2013. On 2016, 3 years later, a core arrived to the lab showing exactly the field evidence of the presence of horizontal fracture. This is from the Eagle Ford. And so it was an Eagle Ford well that was drilled for coring and then was converted into water disposal. It was adjacent to a pad with multi-wells that had been zipper frac and monitored with acoustic emissions, macroseismics. And so the results of the macroseismic and the interpretations was that the fractures were growing predominantly on height. They were going from the lower Eagle Ford all the way to the Austin Chalk without any containment. And yet when the core came up from that coring, we saw several fractures. There's one fracture here, there's this one, and then there is the one below. But this particular one had a substantial amount of proppant. So it was undeniable fact that it was a hydraulic fracture. It has created during hydraulic fracturing, and it had sufficient width such that the proppant went in. With the same conditions, knowing that this is a normally faulting system with the vertical stress higher than the horizontals, how on earth is happening? Well, it is happening. It is happening on laboratory testing, and it's happening on the field. Another test that we did among the various that we were doing in this program was to try to do hydraulic fracturing with proppant, to study the proppant transport and coverage of the proppant. And so this is hard to do on a large block in the laboratory, particularly because the fractures tend to be always very narrow. So this is hard to fracture and transport the proppant. And so we solved that situation by fracturing first with the pad. And once the fracture had daylighted the surface of the block, then we changed the fluid, the much higher viscosity, much higher rates, and then we were able to transport this 100 mesh proppant into the block. But despite that effect, what I want to show you is something slightly different. The wellbore, as usual, was cased and cemented. So we have two perforations. One is here, the other one is shown there. And something that you see in the morphology of the fracture is that around this region where the perforations are, the fracture is very smooth. It's flat and smooth. The rock is the same. It is a layered rock, but the presence of these layers are not obvious seen, right? But they become more obvious as the fracture grows farther away from the wellbore. You can see the traces here. They're small as the povers. They're becoming larger as you go farther and farther. And then that presence, distribution, and thickness of the stepovers get bigger as the distance from the perforation increases. And so the connotation of that is that there is a very large amount of energy for fracture the rock because the velocity is very high. And with high energy, then the rock is overcome and the fabric of the rock doesn't play a role. But as the velocity is coming down very quickly as a function of 1 over r, with the distance from the wellbore, we have less velocity, less energy, and then the rock start making his presence be felt, and we start creating these stepovers. And so that was very telling for us, the fact that when the rock is layered, we should actually anticipate that this will happen. At some point, the interfaces are going to start interacting with the rocks and creating stepovers. And on a second look, I'm thinking now, these stepovers, there is a continuous weak layer on the system, right? But the stepover is not of uniform thickness. In fact, it's narrow here and is becoming wider towards the end of the fault. It suggests to me that on top of that stepover, maybe the fracture is becoming discontinuous, right? You have that phenomena that Ruting Wu and Leonid Germanovich showed in the blocks where they apply some torque. So you're having these fractures that are creating this type of parting with, basically it's a K2 type of fracture. So that was also interesting and surprising. In all these blocks, we had acoustic emissions monitoring in order to investigate what was the effect of the fracture that is propagating, how the fracture is interacting with the interface and then propagating afterwards. I'm showing you two examples. Unfortunately, this one is not running for some reason. This was under low viscosity and low pumping rate. And what you would have been able to see if this would be running is that the fracture emerges from the wellbore, is arrested by the interface until the pressure continues increasing. And at some point, it grows through the interface all the way to the top and bottom prior to overcoming the interface and propagating into the rest of the rock. In contrast with what you're going to see next, which is the high viscosity scenario, where the fracture is generated at the wellbore, it propagates readily into the interface. It becomes more or less localized at the interface as the pressure is increasing until eventually at the critical pressure, then its interface is overcome and the fracture propagates through the entire block. And so the contrast was interesting. In the first case that you were not able to see, the fracture will actually run up and down the interface prior to moving towards the block. In this case, that doesn't happen. Right? The fracture is more or less stable at this point, increasing the pressure until the pressure is sufficient to overcome the resistance of the interface and it propagates. Larry Berman, that was working with the Schlumberger, had a lot of work at TerraTech trying to understand the near wellbore effects. And by near wellbore effects, we're talking about perforating effects. And so what Larry understood very early on is that one cannot drill the block, create a wellbore, and then apply stresses. This is a very different condition than the real condition where the block is subjected to stresses when the drilling is taking place. And so we had for him build a system to be able to do that. So this is the vessel that will have the block, and the block will be stressed at the in situ conditions. And then under this stress, there will be the drilling. And so the wellbore is going to be drilled into the stress system while maintaining the stresses in the block. The casing will be cemented into this wellbore. The perforation guns will be run. Perforation will take place. And after the perforations, then the system will be pressurized to do a hydraulic fracture. So we are simulating the entire cycle of drilling, casing, cementing, perforating, and fracking. And what you see, of course, is incredibly interesting because you see that there are borehole breakouts that are created. The borehole breakouts are going to be interacting with the longitudinal fractures. You are going to have a number of transverse fractures that are emanating from the perforation locations and interacting with the longitudinal fractures that occur along the wellbore. So here is an example. We are seeing the block that came up of the system after the testing. And what you see is the fractures that are daylighting into the external face of the block, right? You have your two vertical fractures that are more or less along the boundaries of the breakouts. And then you have also the horizontal fractures that are daylighting from the block. There is one that is more or less non-linear here at the base. If we peel this block in order to investigate what is happening internally, what you see is now the casing. What you see very clearly is the presence of that longitudinal fracture that is going along the length of the wellbore. You see something extremely interesting. This is the edge of the perforation. And what you see is that the fracture has come up from the perforation as a transverse fracture, and then is turning into a longitudinal fracture above and below. Right? So it's a transverse fracture that is now turning into two longitudinal fractures. And from this longitudinal fracture is emerging another transverse fracture. And so it's a very complicated system. Certainly the stresses are very complicated. And then there is a very interesting, complex connectivity between the longitudinal fractures, transverse fractures that turn into longitudinal, and vice versa. I think I'm going to show you one more example of that, of near wellbore effects. Here the block is being opened in order to show all the features. You can see the casing and the cement. You can see the breakouts. You can see the presence of the longitudinal fractures that are more or less following the morphology of the breakouts. And then at the perforations, you have the generation of the transverse fractures simultaneous to some of these longitudinal fractures that are then becoming transverse, and the presence of some axial fractures towards the end of the wellbore. Very complicated. And of course, it's something that cannot be ignored. That certainly something like that must be happening on the field, even though we tend to ignore it and we tend to consider just a much simpler system. There are some final slides that I'm going to show you that have to do with the initiating fractures from oblique or inclined wellbores. This is not typical, but it was at the time of high interest. How to perforate and how to organize the perforations from inclined wellbores so we can have fractures that are well connected planar with maximum surface area. And so what we did at the time is to create these bigger slots. So rather than using perforations in order to remove the closely near wellbore system, we were creating these bigger slots through the casing to promote the planar fracture propagation, and then investigate how this propagation is, how this fracture is propagating far. So to give you a better knowledge of what we are doing, this is the entire large block, right? 3 foot by 3 foot by 3 foot. You can see the orientation of the casing. We are going to be rendering the hydraulic fractures that are generated in red. We're going to be rendering faults that belong to the block with some colors, in this case gray. And if there are weak interfaces along the bedding, then we're going to render them as well. And we do that with the CT scanning. And in order to be able to do that, what we do is we segment the large block into small little blocks, right? So we call them sugar cubing. So we sugar cube the large blocks. Every cube is about this size, and then it can fit into the CT scanning. It can scan it and provide a three-dimensional view of this block, and then digitally we reconstruct in order to go back to the upper scale. So the reason why you are seeing these little blocks is because this is the area of interest, right? The rest of the blocks are away. You see the region exactly where the fracture was originated from these bigger slots. And you can see that on this particular surface, there was a very nice fracture created, which is planar along the length of this slot. And by the way, something that I might not have mentioned is that the strategy for that block was to create the slots perpendicular to the minimum stress on the top side and the lower side of the wellbore. The slots are, of course, oblique to the inclined wellbore. And this is one of the reasons why this fracture was so nice and continuous on that side. But on the other side, it started nice and continuous and hit this interface, which is presented here, and then the fracture started running along those interfaces. So that's what we wanted to understand, is the not near wellbore effects, and that's why we created these bigger slots, but the close to the wellbore effects. This other experiment is showing you the presence of weak interfaces on the beds, the presence in green of faults within the block, and then the rendering of the fracture that was generated during hydraulic fracture. In this case, the slots were perpendicular to the wellbore, so they're oblique to the stresses. And because of the fact that they're oblique to the stresses, then you see this very large level of complexity near the wellbore. Right? You see this slot here that is generating a planar fracture, but then it connects with this fault on the block and then changes direction. And on the other side, because of the presence of these weak interfaces, you have considerable complexity, right? One side of the fracture is going downwards, the other one is more or less flat. And so you have far more complexity on the lower side of the wellbore, and then the upper side that changes direction because of the presence of weak interfaces. I'll show you one more, which is this one. It's interesting. Again, the slots were constructed perpendicular to the wellbore, so oblique to the stresses, and also on the top and the bottom of the wellbore. And because of the structure of the block, the presence of the interfaces and the presence of the faults, which of course we don't control, they depend on the block. The fracture in this case is much more complicated. It's certainly segmented. It has 3 segments. There is a bigger step over between the lower segment and the upper segment. And then one fracture is reasonably planar. The other one is much affected by the presence of this fault. And you can see the effect of this step over, right? You have one fracture that is lower, then a bigger step over, and then the upper fracture that is growing in that side, that is going to be interacting with the structure of the block and creating quite a level of complexity. And so this is interesting, more interesting, of course, in relation to the propagation, the transport of the propant and other things that are important for fracture conductivity. But that's what I wanted to show you. And I'd like to summarize that with 4 key points. The first one related to weak interfaces. They do influence the fracture toughness. Layered rocks with weak planes exhibit considerably higher fracture toughness than homogeneous blocks. And the ratio of adhesion strength, the tensile strength of the weak planes, to the cohesion strength, the tensile strength of the rock matrix, determines whether these fractures are arrested or propagate less easily. And so if the interfaces are really weak with almost 0 tensile strength, the fractures will most likely going to be arrested, and then they're going to start propagating along the interface. But if that strength increases, then they could propagate through it, but nonetheless, they take some energy of propagation and then make the overall system more resistant to fracture propagation, tougher. Number 2 is that the horizontal fractures can occur despite vertical stress dominance. Large block tests and field observations confirm that horizontal fractures happen even when the dominant stress field, or the dominant stress, is the vertical stress. Now, this is due to the significant difference between the vertical and horizontal stress at weak interfaces. So that was the proposal of Gordon, that is the concept of Grasselli, but also because of local variations in the in situ stress due to the heterogeneity of the system. This is very important, and I think we are ignoring that. We tend to think that we know the vertical stress is rho GH, and we have high confidence on that. And yet we are ignoring the fact that if there is heterogeneity, the vertical stress will not be homogeneous, and they are going to have specific localized regions where the stress is lower than what we think it is, and so it promotes the generation of horizontal fractures. Third, that the complex near wellbore fracture geometries should be expected in hydraulic fracturing. I'm talking about near wellbore. And so longitudinal and transverse fractures were frequently observed in experimental settings once one simulates the drilling, the perforation, and the fracturing. It was in every single experiment that we saw that. And this type of fractures should be considered as realistic outcomes on field operations near wellbore. Number 4, that the fracture behavior under non-principal stress. Now, I was showing you fracturing on inclined wellbores, which is not common, but the results suggest that there is a strong interaction with the weak interfaces and with the orientation of the perforations that influence the way that the fractures grow and interact. And so this will apply, in my opinion, in both horizontal and vertical wells if the stresses, in situ stresses, are not principal, if the shear stresses are present. And of course, that will be the case when you have a heterogeneous system where the stress distributions are no longer uniform. Thank you. That's all I have.